Well, we will start. Hello, everybody, and a very warm welcome to this Ateme webinar, the last one of the year, called Achieving Boundary Savings Using the Latest Video Compression Techniques. My name is David Jarbole, and I'm in charge of business development for Ateme, and I will be acting as a moderator today for this session. As you may know, Ateme is a leader in video compression and delivery, and we are currently working with the most prominent content providers and service providers worldwide. Our solutions enable innovative live on-demand video services for thousands of customers, and basically, where there is innovation, Ateme is there with you. The topic we will address today is how to achieve boundary savings while maintaining the same video quality for your channels, or even sometimes by improving it. I will do the intro of our two speakers today. That will be the next slide, Thomas. So to present and explain this topic, I have with me two of our most renowned experts in the encoding world, and let me introduce them to you. The first one is Michael Rollet. Is our CTO at Ateme. He joined Ateme in 2015 and is leading the standardization effort at Ateme, and is also managing several collaborative projects with the R&D teams. He's following different activities from ITSC to DVB, MPEG, DASHIF, and UHD Forum, for example. He received his PhD degree in 2006. Our second speaker today is Thomas Guillonnet. Thomas is a fellow research engineer at Ateme and is specialized in video processing and compression. He has been working with more than 15 years in the broadcast industry, contributing to design of file and live encoders, preprocessing, and StatMux. He has also been active in GCT-VC and GVET groups for LCVC or VVC standardization, respectively. He received his PhD degree in 2003. Thank you both for presenting today. A quick look at the agenda. First, Michael will give us an overview of Ateme and why we are the pioneer in the video compression. Then Thomas will take over and start by introducing coding efficiency and how to achieve the best video quality possible. Then he'll explain how we can implement it, and he will share more details about Ateme now. Next, he will talk about rate control and StatMux and how to optimize your bandwidth using all those tools. And in the wrap-up, we'll look at real use cases and how some customers managed to achieve more than 20% bitrate savings by using Ateme technology. To finish, we'll have a look at what's next, discussing future codecs, deep learning, and AI, and looking at the benefits that it will bring to the encoding world. We'll have a Q&A at the end, so feel free to ask any question that you may have using the Q&A section. And please also note that this webinar will be recorded and made available on our website in the coming days. Then we can start now. Michael, the floor is yours.
Hello, everybody. So I will speak about the current portfolio at Ateme. So next slide, Thomas. So Ateme is well known for the green bubble, so the contribution and distribution for our encoders, the converged end, the channel origination and our StatMux. And recently we acquired Anevia, and Anevia is bringing to Ateme its skills on the OTT market for the origin packager, the CDN, the DAI, or the cloud DVR. So that's new at Ateme. So we are having the convergence in between what we are more famous at, the broadcast, and the broadband with Anevia. Next slide, Thomas. So something that we are part of, and we are one of the encoder vendors that are part of the two activities. So MPEG is well known from many years now, starting from MPEG-2, AVC, HCVC, and VVC. So we are part of these particular standardization bodies, but MPEG is also well known for the next-gen transport like CMAF, and previously MPEG-2TS, and now also MMT. We are also part of the alliance, so we are part of MPEG for the codec because we are doing our homegrown codec generation, but we are also part of the alliance, looking at what the alliance is doing, and also following the standardization activity there for AV1. So it's a royalty-free codec coming from the GAFA for the web browser. So I have listed at the very bottom of the slide the standardization bodies that we are following. So we are part of ATSC and DVB for the broadcast, MPEG for the codec definition. And recently last year we joined 3GPP for the 5G delivery. But we are also member of the Dash Industry Forum, CMAF Industry Forum, and the Streaming Video Alliance before the acquisition of Anevia, and with the recent acquisition of Anevia, it makes even more sense to be part of this group. Something that we are following and that is also related to the end of this presentation is the Media Coding Industry Forum that is looking at the patent pool regarding the latest codec from MPEG that is versatile video coding PVC. So next slide. So just some dates. So we were chairman of one of the working group for HEVC in 2013. We are part of the alliance since 2015, and we were contributing thanks to a collaborative project on VVC with several French partners. And we are also following AV2, so starting the activity with AV2 still this year. We are following still some forums, so with the Ultra HD Forum, the VR Industry Forum, or the Media Coding Industry Forum. On the innovation side, so Thomas will come back to this at the end of this presentation, we are also working on AI. So UHD, HDR, and next-gen audio is one of the topics we are covering also in my team, and we are looking at 5G, 8K, and beyond UHD. So for that, we have several collaborative projects that we are setting up to fasten these implementations in general. So Thomas, now it's up to you for the latest slides.
Okay, so thank you, Michael. Thank you, David, for the introduction. And hi, everybody. So I'm going to first give some general points about just basic video quality. And then I will try to explain you how we do the effort we have to put to achieve good video quality in an industrial video encoder. So first point, we are using a codec. So let's say, for example, HEVC. So when we look at a codec as it is developed by standardization bodies, we just look the relationship between bitrate and quality. So that is, the more bitrate, the better quality it is. Of course, it is a lossy codec, so we are losing some parts of the information when compressing. And so we have to monitor the quality. So here, what we can see on this slide, it's a comparison between a verification model and so for HEVC, called the HM, and our own encoder, configured to give the best possible quality in order to be compared to the verification model. And what we can see is that we are on par. So I would say so far, so good. We are as good as a reference. So that sounds good. And we are even much faster. And there is a reason for that. So let me tell you. Now, if we consider the real world encoder implementation, we are not concerned only with just raw performance of the core codec, of the core video compression standard. So first, we have speed constraints. We have to be real time, that's a simple fact. And what does this speed constraint mean is that it means that we have to use powerful platforms, powerful CPUs. It has an impact on density, how many channels can we pack in a platform, and more importantly, it has an impact on quality. So yeah, video quality, what do we call quality? In the previous slide, I was showing some objective metrics results, but what we expect is a high visual quality. So what the end user, when you are watching the TV, what do you expect at quality? This is something visual. This is something very human. This is the quality you as a human perceive. And yeah, conversely to the previous point, it is depending on available CPU, so the power you can make in your computation, and also software optimization, so how you design and implement your software, and finally control. So what do I mean by control? This is control of every parameter you have in a video encoder. So that's rate control, controlling the rate distribution, rate allocation inside a frame, between successive frames, and even between different video contents. And it's control of the algorithmics, how you tune. At some point, you have a limited complexity. If you want to achieve optimal quality, you need such an amount of power, of CPU power, that you cannot do it in real time. So at some point, you have a trade-off. You have to compose with these constraints. So in short, the video quality depends mainly on 5 criterions. So bitrate, how you control this bitrate, how you distribute the bits, how your encoder is designed, the CPU you can access to, and also the input complexity. I mean the source input, the video input. Depending on the kind of input you have, it impacts also the ability you have to render video quality. And so here the important message is that video quality depends on all these factors when considering compression, but also all these factors are interacting with each other. I mean, take a simple example. If your input complexity is small, you may achieve a good quality while consuming less CPU power. That's an example. There are relationships between all these parameters, and that's very important. So, I mean, we have to put effort in all of them. Let's have a closer look. So, input complexity is quite straightforward. I mean, if you have just some talking people sitting on the desk or a very animated sports sequence, then it's not the same amount of information. Bitrate, of course, you know about it. And encoder design, that's an important part. So a video codec, you can think of it as a toolbox. So a video standard like AVC, H.264, or HEVC, they define a set of tools so that you can apply at elementary parts of your images. So the goal of the encoder is to pick the right tool at the right place. So considering any block in the picture, you have to say, okay, I want this tool. I want it to be intra. I want it to be inter. I want it to be skip. I want it to be partitioned. I don't want it to be partitioned. That's something the encoder has to do. And there is a very high number of possible combinations. So that if you want to check all the possibilities to make sure you are picking the best one, then you have an incredibly high number of combinations, and it's just not tractable. You cannot do that. Therefore, you have to design algorithm, heuristics, you have to optimize. So that's how you reach this density quality trade-off. So in the case of Ateme, we have this fine-grained complexity tuning, what we call elasticity. That is, we can adapt to the platform. We change dynamically, we change the way algorithm works in order to adapt to conditions, input complexity, or change of platform. I mean, if you are adding a channel on a platform, that means you have less CPU for all the channels which were already there. So we can adapt to that with graceful change in the video quality. And finally, rate control. I will come back on that later. So let's move on to the first part. Implementation on Ateme now. So I mean, so I said we have many constraints to deal with, and the important message here is that a video encoder as a Titan Live, as we are selling it, it's not just a core codec. It's not just a standard like HEVC or MPEG-2 or H.264. you have many, inside the encoding cores implementation, you have many tricks and algorithms we have to develop, and outside, we have also many steps we have to go through. So here, it's the actual architecture we are implementing. Preprocessing, which can be of two kinds. That's mandatory preprocessing, like if you have to change the resolution, okay, this is what you have to do. Or optional preprocessing, something we do to improve video quality. Preanalysis is of paramount importance because it's used to pilot the rate control and also to pilot a certain number of algorithms inside the encoding core. So to know in advance about the sequence and use optimal tuning adapted to the sequence. And finally, rate control is also very, very important. You can have huge quality differences depending on how you distribute the bits among the video. So to make it clearer, yeah, so if we try to give some figures, we have many algorithms implemented in the Titan Live. So for each part I mentioned before, for example, preprocessing, more than 15 tools available. For preanalysis, the same. For the core coding part, just speaking about tools and algorithms which are dedicated to optimize the visual quality, that is how you perceive quality as the human. We have more than 30 tools and parameters. Actually, for the encoder, there are hundreds of hidden parameters you have not access to. That's all piloting small tweaks or variation in the algorithm. For rate control, I'm not giving figures. I just want to say it is codec agnostic. So we have a rate control module which is applied on all codecs, and that is it is predictive. So we are able. This is very important, especially for StatMux. We are able to predict the behavior of an encoder before doing the encoding. And just as an information, we use machine learning to do that. So that's basically the message. Is all of that is a lot of tools and algorithms. So maybe it's not very clear to understand what is this. So let me give some examples, simple examples. So let's talk about preprocessing first. This is an example of motion compensated temporal filters. That is, it's a denoising filter. So if it can clean several kinds of noise. Let's say you have some noisy patterns in your video, or potentially some quantization noise coming from a previous encoding. Then this filter is very, very efficient. So you can clean the video and input a simple content to the encoder. At the end, it will ease the work of the rate control. It will ease the work of the decision module. And on the final output, you will have something cleaner. So this is a way, before doing the actual compression, this is a way of cleaning the content, of helping the video compression and achieving better video quality at the end. Now, yeah, this kind of preprocessing, the interlacing, is more like a mandatory preprocessing. So if in your application you have to move to progressive content, then you will need this, the interlacing. So it is just to mention that we are providing a high quality. The interlacer, we have been spending a lot of energy on this, and we think that it is very important to avoid artifacts that can be easily happen with like these jiggies we are showing. Yeah, it's correcting that. It's quite tricky. So we spent a lot of energy on this. So here is another kind. So preanalysis. Here we are doing an analysis which is dedicated to human. So by looking for skin tone color, we can identify areas which are populated in the image by human faces, mainly faces. And this information is meant to be provided to the encoder. At some point, as a human being, we are very sensitive to a quality in the, on the human faces. So we want to do something special for that. And it starts with analysis. Here is a completely different kind of analysis. So flash detection. Flash happens in many situations. It can be like in that example, in a show, you have flashlights, but it can be something else. It can be a very short event happening on one frame, like someone going in front of the camera or whatever. It's an event which breaks temporal continuity, which an encoder relies on the prediction. When encoding a frame, an encoder relies on the previous frames to make its prediction. And if you break the continuity, then you may have quality issues. So to act on that, we first detect this kind of event. So that's analysis. Now let's move to inside the core codec. So as I said previously, there are many decisions to make in an encoder. And so that's a key point. And before talking about analysis, even the basic block decision, this is something we have to be very careful with. So at the core of what we are doing here is the fact that we are able to predict what will be the effect of an encoding on a block, and the fact that we have an internally developed quality metric. We rely on that to make sure that the consequences of a decision is well handled and that we know how it will be perceived by the user. So basically, this is the first criterion on which we perform optimization to improve the overall visual quality. So, and this is very important. On this example, you can see, depending on just inter, intra, and skip, so that's, let's say that's the three basic decisions. There are many other combinations, but the three basic decisions. On this decision, you have to be right. You cannot get wrong on this because you will see it. Bad things will happen. So this one is at the frame level. So that's interesting. At the frame level, you may know that we have several kinds of frames. So iframes are very useful to start a stream or to change channels, but they are also costly. So we don't want to put many of them. P frames and B frames are much smaller, but for B frames, there are a lot of temporal dependencies and maybe eventually from further frames, not immediate following successive frames. So at some point, it's very important to dynamically decide where you put frames and what kind of frame. And especially if you have a flash, you certainly do not want to put an iframe before a flash, for instance. So this is where the analysis I've been talking about is coming into place. So it helps deciding, among other things, this flash analysis help deciding where you put what kind of frame. And the same goes for adaptive quantization. So this is where all we spread bits inside a frame. At some point, we want some part of a frame to be of better quality than others. And what parts? Here, in this example, it's very clear. We want the face to be of better quality. Having the water sprinkle a bit degraded, it's not important, but the face, it's very important. And we have these tools. We know there is a face because we know there is skin color here. So we can act on that using quantization tuning. So that was a few examples. On this last slide of the section, I want to give a bit a different example. Additionally to all I've been explaining, there are also special features you may want. And this is an example of very special feature, film grain synthesis. So film grain is a legacy effect. So when you capture movies with actual film in the good old way, analog way, you have grain on your picture. You have these patterns. So yeah, it's nice. You may like it, have this effect. But the problem of grain is it's a kind of noise, and you cannot compress it. That's not possible. So it's very difficult to handle in a video encoder. With film grain synthesis, we have a very straightforward idea. That is, you can analyze the grain, remove it, then encode a frame without grain, and just synthesize it on the encoder side using a random generator with appropriate parameters. And this is a very effective method. The gain is huge, but the analysis part is quite challenging. And why I'm talking about this is because this is not a new technology. It was present in H.264, but in an optional form. In the new codec AV1, this technology is present in a mandatory form. So if you have an AV1 decoder, it should be able to synthesize grain. So that's a very interesting special feature. So let's move to rate control. I want to spend some time specifically on rate control because it is of particular importance to the resulting quality. So first, the basic principles: all video contents do not contain the same amount of information. That is, you have complex video sequences like sports. You have very simple video sequences like talking heads. And if you want to achieve a constant bitrate, then you have to adjust to that. That is, if you are in a constant bitrate, you have to adjust the way you quantize, the way you process the video, so that the bitrate stays the same. But the fact is that you will have to vary the quality. So if your bitrate is constant, complex content will have lower quality than simple contents. On the other hand, if you allow moving the bitrate, then you can achieve constant quality. But obviously, complex sequences will need more bits to achieve the same quality as simple sequences. And if you apply this principle of a single encoder, you have rate control. For example, CBR, constant bitrate. And if you apply this principle on many encoders, you have statistical multiplexing, that is StatMux. So let's have a look. This is a summary. Let's say we have two sequences with rate distortion curves associated to two sequences, and we are in CBR, so we have the same bitrate for the two sequences, that's 1.5 megabits. So we have two different qualities resulting from that. Let's say we have a StatMux looking at the two sequences and saying, okay, I want the same quality for both. Then the StatMux is allocating a different bitrate for the two sequences. So the two sequences have each their bitrate, but they have the same quality. And we can see, what we can see here is that we gain quality on the complex sequence. The complex sequence has more bitrate and is of much better quality. So that's why we are gathering several sequences in StatMux pools, and we do it in a way to have diversity so that you can allocate few bits on some sequences and a lot of bits on other sequences. That's a very effective method for reducing the overall bitrate, the overall average bitrate affected to sequences, to channels. And regarding this StatMux, so how does it go in an Ateme product? So we have, in this example, Titan Live and Titan Mux. So the StatMux is implemented in the Titan Mux. So Titan Live and Titan Mux have to communicate. It is, of course, an in-house implementation. I mean, you cannot plug StatMux from a vendor to an encoder of another vendor. It is not possible because you need a common API, and more importantly, you need algorithms that understand each other. So the StatMux algorithm inside the Titan Mux knows the characteristics of the video encoders inside the Titan Live, and the allocation is made depending on the statistics, on the information provided by the Titan Live, knowing what the encoder characteristics are. And that fact is very important. And this is a real-time process. So here it's written every 40 milliseconds, but it can be faster than that. Think about for every image, we reallocate the bitrate. And we have, so why it is important to have this communication? This is also because Titan Live can have information about the network characteristics and how the MUX is going to process. That is, when allocating bits among different channels in a StatMux, we are taking into account the fact that there will be some bits dedicated to packetization, for example. And that's very important. So we are actually doing things to make sure we are using the whole bandwidth. There is no stuffing in our StatMux, if you want. So think about it. We can have StatMux in a static mode, still taking into account the packetization bit rate. And this is, if you have some input data stream for many reasons in your, for example, on your transponder, then you can move to dynamic mode. We are proposing that is the overall bit rate of the StatMux is going to adapt to the data streams. So not only the bit rate per channel is going to move, but the whole bit rate of the whole StatMux is also going to move in order to adapt to the input data stream and to always occupy the whole bandwidth available. That's a very important point. So what does it do? When we implement this in real life, so we go, we have access to many productions from customers, and we can do some analysis. So the idea here is to show you some analysis that has been performed on customer sites. So comparing a production, an existing production, to what we are bringing with our current Titan solution, I mean. Titan Live, Titan Mux. So let's move. And specifically, we are interested in StatMux because, of course, people are using StatMux technology. So in this first example, it's just to give you the idea, how do we measure improvement? We look at video quality and we look at the number of channels we are packing in a given bitrate for a StatMux. So that's basically how that's the two metric we need. So basically the number of channels gives you the average bit rate, and the video quality, you have to look at it. And in this example, we had at a European customer, we had an existing production and we provided 3 configurations with the green bars indicating the additional channels. And we could improve the video quality while adding some channels, or we could keep the same video quality while adding even more channels. And at the end, it amounts to a 20% bitrate saving, equivalent to the number of channels added. Here is another example. This one is for MPEG-2 SD at a European DTT broadcaster. And we went, it's the same principle. We start from a production and we can add channels and see at some point if we have better quality or same quality. And in this example, we went from 11 to 14 to 16 channels. And that's as high as 45% bandwidth saving in this example. So we are very happy with that. And the explanation for this bandwidth savings is in all the technology I've been presenting previously. That is core coding technology, preprocessing technology, StatMux technology. It's a sum of all this which makes the gain. So here is just a picture illustrating this. Actually, we are going from 11 to 16 channels, and the quality is still a bit better than the original production. So we are very happy with this result. Same story here, but this time another customer, DTH broadcaster, H.264 HD, and a huge transponder of 60 megabits per second. And in that example, we went to 37 to up to 44 channels. That is equivalent to 20% bitrate savings. And same explanation, it's a sum of all technology. And especially the technology I've been talking about StatMux, So the fact that we avoid all stuffing, we always take into account the packetization cost in the StatMux allocation, and the dynamic StatMux, the fact of adapting to information stream, data streams, we could save up to 2 megabits per second. That's a lot. And one more little thing, we have this enable still picture feature. At some point, this is a quite common use case. You may have to black out for some moment, you may have to black out some channels. And we have a feature for that to minimize the cost of these blackout channels. So these channels are still online, but they cost very few bits, and we have savings associated to that. So yeah, so we accumulate many ways of saving bits to achieve this final result. So if I try to summarize the situation here, so you have quite wide bitrate ranges here. It's because gains depend on many factors, and I've been explaining that at the beginning. So it depends on the kind of contents you have. It depends on the size of your StatMux, if you have StatMux. It depends on your codec on resolution, and it depends on your level of requirements, depending if you are talking with a regular channel with good quality or premium channel with especially high quality. So it's up to you to position yourself inside the range, the bitrate range, which is possible among for each situation. But at the end, what you can see here is that it's possible to really go to very low bit rates with a very satisfactory quality. So that's, yeah, the summary of what I've been observing in the analyzing the customer use cases and results. Now, we have a status on what I've been presenting in the previous slides. It's bit rates we can achieve currently with our current production products. So how is it going to move? So there are two factors which are illustrated here. First, for all the algorithms, all the many algorithms we are working on, it's a continuous effort. We are always trying to improve little things by little things and to have gains. So even an old codec, even MPEG-2, we can still have improvements on MPEG-2. On this graph, I represent H.264 in yellow. So H.264 is a very mature codec, a very mature implementation for us, but we are still thinking about improving it. When you have a new codec, you can have a big gap, but not immediately. There is a time to reach maturity. So you may have first an implementation where the gain is not very important compared to the previous generation, and then as you improve it, you reach the big gap between two codecs. And this is exactly what is happening here. If you look at this year, 2020, with the green vertical line, this is exactly where we are. So this graph is a trend. It's an indicative indication how it evaluates on any content. And so we are here with this VVC implementation, which is a very early implementation, which is close to HEVC, but which is going rapidly to improve and provide the new gap compared to HEVC. So yeah, what's next? So what you have seen here is the current, the effort we put in designing our encoders and the current results. So how do we improve on that? Well, first we have new codecs. So the situation is a bit different compared to before. We don't have one successor for HEVC, but we have several contenders. So let me tell more. VVC, for versatile video coding, is the official successor of HEVC. It has been developed and standardized by the joint ISO ITU group, GVET. It's kind of the same process as for HEVC. Same process, more or less same people, And so that's the next generation codec. But there has been a situation with HEVC and on licensing terms which were complex and unclear. I don't want to develop on that, but the adoption of HEVC has been slowed down by confusing licensing terms. So companies from the GAFA, Google, Facebook, Amazon, Netflix, Mozilla, many companies. It's a Google initiative first, but that's many companies together which have formed an alliance, AOM, and they have created AV1. And the main characteristics of AV1 is that it's a royalty-free codec, so no licensing term. And finally, during the VVC standardization process, another codec emerged, that's EVC for essential video coding. And so it has emerged because maybe of the worries we may have that VVC suffer from the same problem as HEVC. So people want VVC to have clear licensing term, but what if we do not succeed in that? And people created EVC, which is meant to be royalty friendly, not royalty free. It's not the same as AV1, which is a standard, and which should be, which is expected to be, if not as good as VVC, but still a good state-of-the-art codec. So instead of having one next codec, we have 3 of them here. What do we do with that? Well, to be clear, the real successor of HEVC is VVC. That's the largest bitrate gain. Of course, there is a complexity price to pay for that, but this is the best performance codec. And additionally, it has some, yeah, I didn't precise. Let me go back to the previous slide. So VVC, the first V is for versatile, and that's because from start, VVC is including several tools dedicated to virtual reality, to scalability, to screen content coding, to low latency. So that's a lot of feature additionally to the usual fact of reducing the bitrate. So VVC has this best performance for it and this very useful versatility. And we know it will integrate smoothly in the usual processes because it's like HEVC. AV1 on its side is not as good in terms of coding performance, but still there is a coding gain compared to HEVC. And it is royalty free, and it has this film grain synthesis, which is for the first time mandatory in Encoders. So this is a useful feature we have to consider too. And EVC, oh, there is a typo on this slide. So EVC is not 41%, doesn't exhibit 41% bitrate gain. The actual figure is not 41, it's 27%. So please accept my apologies for the typo. So for EVC, we have quite a good coding performance complexity trade-off, but the usefulness of EVC will depend on the success of VVC. If we have no licensing issues with VVC, then we are not sure that EVC is useful at the end. So time will tell. On Ateme side, we are implementing what we think are the most promising codecs for now. So we have an AV1 implementation, which is currently under development. So it is on par with HEVC. So there is still some development to make it better than HEVC. And we have our own film grain analysis implementation. We have a very early development of VVC, and we are very happy with that because the standard has just been finalized this summer, and we already have a live implementation, which is a bit better than HEVC, and which can do 4K. So we are very happy with this implementation. And just to mention, so these are the AV1, VVC, EVC are the current new codecs, and people are already working on the next generation, which will be AV2 and something post VVC. And people are working on deep learning based codecs. That's very important technology nowadays. So let me give a couple of words about deep learning. So first, definition. You may have heard a lot currently about deep learning, machine learning, or artificial intelligence. So what is what? Artificial intelligence is a very wide field of computing science, and it includes several subfields. And one of these subfields is machine learning. So the idea of machine learning is to solve real-world specifically defined problems by automatically learning models. So it's not exactly intelligence as you may think as a human. It's a way of solving problem by learning the solutions automatically. And then from machine learning stems the deep learning, which is the same principle, but with much more complexity. So it was not like 10 years or 20 years ago, it was not really possible to do deep learning because it requires not only appropriate algorithms, but also quite a lot of computing power. And now with modern GPU, you can do quite complex deep learning on a regular PC. And it opened a lot of possibilities, and it's a highly successful field nowadays with many successful applications of deep learning. So for some reason, it's not yet very used in the field of video compression, but it's starting. So what do we do as Ateme here? We are working in we are currently working on the deep learning topic, and we even got a funding for that. We won this innovation contest grant from France, and we have a very ambitious goal here, which is to work on both the coding core, both the pre-processing part, and both in the cloud part and outside of the Titan product. So the idea here is that we know that every part of what we are doing can benefit from deep learning. And so what are these benefits? For pre-processing, so you can see here the same structure as on the left, the same structure as a Titan Live encoder. So for pre-processing, we can enhance the quality of the processing thanks to deep learning. For pre-analysis, this is particularly useful. We know that we can improve robustness of our pre-analysis and even add new features like reducing latency by predicting future behavior of frames. This is something that only deep learning can do. We can improve reliability of rate control. We can use it in core coding to speed up file encoder or to improve the quality for live encoders. That's two complementary ways of seeing things. And finally, we can apply that to cloud and orchestration. That is, when you want to deal with many channels, like hundreds of channels, and you want to distribute them on the cloud, at some point, you may think about the StatMux ID and say, okay, do we need the same platform for all contents? Do we need the same CPU for all contents? Do we need the same bitrate? Everything, every parameter. And this is a huge optimization problem, which is very difficult to solve. And that's why we want to rely on the artificial for that. And the end result would be to minimize the cloud cost, because if we optimize the way encoders are distributed among the cloud, then we can minimize the quantity of CPU power used to achieve the desired quality, hence minimizing the cloud. So that's a very promising technology. And that concludes my talk. So I thank you very much. And I think we can answer to questions. So I let David take the lead.
Mm-hmm. Thanks a lot, Thomas. Thank you very much for this presentation. We have indeed quite a few interesting questions. So let me start with the first one. The first one is for the current technology. Are the bitrate needed on MPEG-2 equal to H.264? Or is it better on H.264?
It is obviously better on on H.264. Is there any confusion with this? I think we had quite good improvements on MPEG-2 even recently, but still H.264 is better. So at some point, if you see in the tables ranges which have common bitrates, that because it depends on your requirements on video quality. But at equal bitrate, H.264 will be better.
Mm-hmm. Thank you. Another question for you, Thomas. With EVC, are we going also to support LCVC?
Okay, so thank you for this question. That's very interesting. LCVC is quite a different beast. LCVC is not a codec as we mean it usually. LCVC is an enhancement codec. That's what its name means, low complexity enhancement video coding. So it's a MPEG standard which specifies only an enhancement layer on top of an encoding performed by a classical codec. So let's think about HEVC. So you have a video content, you don't scale it by a factor of 2, and you encode this downscale version with HEVC. So far, you are using existing standard tool. Then LCVC provides means of upscaling and residual to go back to the full resolution. And so it's much less work. At some point, if we have to support it, it's much less work because a lot of the work is in the base layer, which is standard codec, which we are already working on. Now the point is we are not focusing on this now because we are not sure to see the actual use cases. And we know that the performance of LCVC is highly dependent on the base layer. So as we have the technology for the base layer, so we are already ready if needed. But we don't have really use cases for LCVC for now.
Thank you. Another one. What can we expect in ultra low latency for remote production with the new codecs in comparison to H.264?
You said ultra low latency, that's it?
Yeah.
Okay.
What can we expect?
Okay. Yeah, for ultra low latency, I would like to mention 2 technologies. And there is, for VVC, there is this GDR technology, that's gradual decoder refresh. So this is something we were doing before. That's a way of not coding intras, but spreading intras across several frames. But for the first time in VVC, you have specific syntax tools to improve that technology. So this is meant to achieve ultra low latency. And so maybe you were talking about contribution in your question, because there is also
the remote production, yeah, absolutely.
Yeah, because there is also, but it's for distribution. I was about to talk about CMAF low latency, but I think it's not the question. It's for distribution. Okay. So yeah, you have this GDR feature for VVC, and that will be helpful. And other from that, we will rely on usual technologies, I guess.
So the question about the StatMux, by using StatMux, what is the latency increment?
Yeah, that's a very good question. There is indeed a latency increment, which is approximately the size of the VBV. So that's about 1 second on average, but it depends on the codec configuration. That's, yeah, it's the size of the encoding buffer, which is used to smooth the bitrate variation. We have to take a step in advance for communication and to make sure we are respecting bitrate constraints. Because, you know, in a StatMux stream, you may have, like for each channel, you may have a maximum bitrate to enforce, and you have a VBV to smooth that. And yeah, you have to respect this constraint. So I would say on average 1 second.
All right. still on the StatMux efficiency, how many pools should we set up for 1TS with different genre of channel? There's a detail associated to that. Should we make a different pool for sport channel only? So in 1TS, we'll have more than one pool of StatMux. So I guess the question is more, can we mix different type of channel in one pool of StatMux?
You
mean
any
recommendation?
I'm not sure to get the point. Different type of channels, what would it be?
Could we, I believe the question is more, could we mix different type of channel into a pool of StatMux to gain the maximum efficiency, or would you recommend to have like a pool of sport channel only?
Okay. So the more channels, the better. That's a simple rule, and it depends on what you mean by types of channels. But if you want an efficient StatMux, you better mix different types of channels. That's the way to go, because you have at some point you need an exchange of bits between channels to others. So you need to have channels which cost less and channels which needs more. So yeah, you have to mix different type of channels. But that's I was just confused because there is another thing I didn't talk about, but we have technology to mix different resolutions and different codec in the same StatMux pool. We are able to do that. We have been experimenting that. So for example, we can mix 4K on HD. We can mix H.264 and MPEG-2 in the same pool. We know how to do that, but there are at some point more complex constraints to be efficient in that case.
So maybe still one related to the StatMux also. Are there any limitation when combining SD and HD channel in single H.264 StatMux?
So yeah, basically just what I'm saying. So we can perfectly do that, and yes, there are limitations. If you don't have the right balance between SD and HD channels, you may not have the appropriate flexibility, and you may end up with a channel with a very small range of variation, which is not desirable. But this is something which has to be defined not generally like we are speaking now, but we have to look at the use case to give a recommendation on that one.
All right. I have one that is a bit more general. Do you envisage StatMux and encoders from different vendors interoperating in the future?
No, we are not considering that. I think it would be very difficult. Nothing is impossible, of course, but we would be losing some specific features, some specific quality improvements. So I think it would be less efficient.
Okay. I'd like to talk a bit about VVC. We have a few questions about VVC. Is VVC driven by 8K as X264 was for HD and HEVC for UHD?
Well, I am not sure to have the right answer. I would say that the other way around, if you want to do 8K, VVC is necessary. And we have studies on that, and we have proof of that. We have documents which are available. Now, I think VVC can exist even without 8K, because there is a lot of pressure on bandwidth currently. And if you want to generalize 4K, and both for broadcast on VOD, both for OTT and on broadcast, VVC might come and be.
All right, another one on the VVC. Will there be any delay in the latency when the VVC runs side by side with the current encoder and decoders in HEVC?
No, there shouldn't be any. You mean delay like latency difference?
Yeah.
No, the structure of the VVC is the same. The main structure of VVC is the same as the one of HEVC. So the implementation principle, it's much more complex, but the implementation principle has to be the same. So the latency should be the same.
Okay. Another one, so on the next gen codec, are we working on developing SHVC encoders?
Oh, yes, we do have an SHVC encoder. And we have been demonstrating it. Maybe Michael can tell more about it. I think it has been demonstrated in US. But yes, we do have an SHVC encoder working.
I'm not sure, Michael, if you want to add anything on that. Or... No need. Another question, interesting one indeed. If we have different kind of input for some channel, mix between SDI and IP, is it better to make this as different pool, or can it be the same pool?
I'm not sure to have the right answer, because that may not be my part.
Mm-hmm.
On the principle, I would like to join them in the same pool.
Mm-hmm.
I mean, if you can have a bigger pool, you should fill it with as much channel as you need.
Mm-hmm.
So, but I don't. Maybe I'm missing something. I don't see any technical constraint. At some point, you have some synchronization issues, maybe.
Mm-hmm.
But yeah, once encoders are fed, two encoders having a different feed, they can still communicate with the Titan mux, and I think it should work. I don't see any problem with that, but maybe people from the product team could also answer on that. That's a very interesting question. So my answer would be yes, you can mix them, but I would check practically if I had to do it.
All right. Another one. Let's keep going. So we passed the time, but we'll finish up a few more questions before closing this this presentation. Are there any similarities between StatMux technology and content adaptive encoding?
Yes, there are. Yeah, that's a very nice observation. At some point for content adaptive encoding, we are doing some predictive, predictive rate allocation, and we are doing the same for StatMux. So behind this technology, we have the Ateme quality index, which is our internal metric, which is the same for both technologies. And it's a bit more tricky for content adaptive, because we have to deal with resolution changes and even frame rate changes. So we have more parameters to predict. So it's a bit more tricky, but yes, this is the same principle.
All right, excellent. Another one on VVC. What's the minimum latency when you use VVC? Yeah, go ahead. You want to add anything on that?
Yeah, I think we already had two questions. So I see you people are interested in latency. That's good to know. So the same latency as other codecs is to be expected with VVC. That's what I said before. So I don't have figures to give, but I mean, we are flexible with latency. We can configure it in our encoder, so it depends on your use case.
Okay. And let's have a last one related to AI. Is Ateme using AI or machine learning in the codec?
So there is a machine learning in the rate control part, and especially for the predictive part. And for other learned models are quite simple in the current codec. So deep learning is more on the research track now, but we have promising results. And I think VVC will be the first codec to fully benefit from AI in the sense of deep learning some really complex stuff. Because you know, machine learning is a vast domain, and you can do simple machine learning, you can do low complexity machine learning, So the current step we are observing now is that we are moving to complex learning, deep learning.
Okay. Excellent. So, well, I guess this will conclude this presentation for today. If you have any more questions, you can reach us using this email address, sales@ateme.com, or your local Ateme representative. Don't hesitate. We definitely can reply to this question and follow up with you. This presentation will be made available on our website and on our YouTube channel in the coming days. And I guess that would be it for today. Thank you very much, Thomas. Thank you very much, Michael.
You're welcome.
And I wish you all a good end of the day wherever you are in the world, and a very happy Christmas because it's coming very, very soon. See you soon.
Thank you, Dave.
Bye-bye.
Thank you. Bye.